Welcome to the first of the two lectures of Markov Decision Process. So this lecture will mainly focus on the top three topics, which are states and what is Markov besides being a cool name. Third are the Markov processes, and we'll go through a very basic introduction of Markov reward processes in the same video, but we'll discuss it in detail in the next one. So before we start, right, do you remember Robbie? So Robbie was this really cute robot who was trying to learn how to walk in this maze. So while doing so, Robbie was making intelligent observations such as angle of orientation, the speed, where the wall is, and the sensory information that was being fed, that was being transmitted by the sensors we have placed on Robbie. So all of these together, when grouped, we can term as observations, right? So does it make sense to you when I say that these observations are enabled by an observable environment? Does it make sense when I say that not only Robbie and the sensors and its whole features that Robbie comes with, in addition to that, these observations are enabled that because there is an observable environment. So what do I mean when I say observable environment? So when an agent can determine the state of the system at all times, it is called fully observable. So it might seem a little daunting at first, but let's just think about a scenario. Let's just imagine you walking down the road, and I've given you one task. You don't have to, you can't bump into anyone, you can't collide with anyone. And how do you do that? So in the middle of the day, you have plenty of information. You have all of your five senses, and there's plenty of light, so you can see everything clearly. You can see where your fellow pedestrians are. You can see oncoming traffic. So it's very easy to, not bump into someone. But if I do the same thing, if I tell you to do the same thing at night where there is total darkness, so even when you are still able to see, hear, touch, feel everything, like all these five senses are still there with you, but the environment is not enabling you to take in all the information that you actually need. So we can say during the day, the whole environment is fully observable, whereas during night, it is partially observable. Now we'll look forward into what a state is and take a more intuitive example for the same. So in the previous video, I defined state as a necessary information about the environment to make a decision observed by the agent, right? So let's take a very natural example for the same. So Mario, right? Every one of us has played Mario. If you have not, I'm really sorry for your childhood. But in Mario, what he's doing is he's trying to level up to ultimately save the princess, right? So the agent or Mario is interacting with the environment to do the same. And what, according to you, will you define as the state of a Mario game? So, state can be defined in so many different terms. It can be defined as Mario's position, it can be defined as the level Mario is at. According to me, the information that would entail everything, every necessary information that we would need to help decide Mario what to do next would be in that screenshot of on that particular time step. The screenshot of the game at that particular time step would be a perfect description of state. It would contain the score, it would contain all the obstacles that Mario has in front of him, or at least the obstacles that we can at least see. And hidden breaks, bonuses, rewards, everything will be encapsulated in that screenshot. So state can have a broad description, but it is best to find that boundary or to find that perfect definition of state that will help us, that is more relevant to our problem statement. So let's see how states and actions come together. So let's say that we are in an initial state 1 and we undertake an action A. We observe that we move or we transition from a state 1 to state 2. So we can take a very natural understanding from this that transition in state occurs when we undertake actions. All right, it's a very simple, like I think a very intuitive understanding too. So we will see a chain reaction for the same understanding or the same approach. Let's say that we are in state 1, we undertake an action A1, we go to state 2. Similarly, state 2 undergoes an action A2, transitions into state 3. What I want you to do is I want you to draw your attention to this transition itself. State 6 undergoes an action A6 and comes back to state 1. Now I'm going to ask you a very weird question. Are these two states the same? So the way I would have answered this question would be yes, they are same because they are named the same. But no, it's more than that. What I'm trying to ask you is, in this case, state 1 was an initial state. In this case, state 1 has undergone 5 intermediary states. So do you think that this state would consider, like this state 1, this version of state 1 would have more information as compared to this state? Or are these two states the same? Essentially, if they are Markov states, both of these states are the same. And it's very interesting to actually build an understanding of this. Let's take another example. Before even defining Markov, let's take another example and see and build an intuition or build an like understanding of the concept of Markov properties. Let's say we are interested in this state S and we can reach this state S through three different roads: a red road, a green road, I guess, and a blue road. So all of these three roads are mutually independent, right? They have no connection to each other. So what I want to ask you is that the information that is stored in state S when we enter it through the green road, is it different than the information that state S would contain when we enter it through the red road? The answer is no. The information that the state S would entail or would contain within itself will be independent of what states it has gone through to reach state S, right? So, a very famous Instagram quote, I think almost all of you would have heard, is the future is dependent only on what you do in the present, not in the past. So, this is what Markov property tries to say. It says that the present state entails all the information that is necessary to characterize what you want to do or what decision you have to make. All that information that you would need is in that present state itself, and you do not have to worry about the history or how we got to that current state. So, this is the same expression with just a formal definition. I will not read that out loud, even I don't understand it. So, let's focus on this expression here. The expression states that the probability of the future state or the state at t plus 1 conditioned on the information that the present state is s of t is equal to the probability of the future state conditioned on the information of all the states that have been visited in till time step t, which means that the information that the whole history of states is giving us is equal to the information of the current state itself. So we do not even have to worry about the history, right? We just have to worry about the present, and we are good to go on any information that we would need to take any decisions on the future states, right? So that's what I mean by Markov property. So what is a Markov process? So Markov process correctly to correctly categorize it would be a random process. It is a random process with states having Markov property. So Markov process is a process with Markov states. It's as simple as that. So let's take a very simple example. So we have four states here: S1, S2, S3, S4. So I have denoted terminal states by squares and circular states by non-terminal states. So terminal states, what do I mean by them? Terminal states is self-explanatory that the process ends there. If any transition of any state leads it to a terminal state, the process ends. So in this state, we can see that the state S1 has probability for each transition. So the probability of transitioning from state S1 to S2 is 0.3, transitioning from state S1 to S3 is 0.2, and S1 to S4 is 0.5. You sum them up, you will realize that the probability is coming to be 1. And that is because we know all the possible states S1 can go into, right? So let's take a little bit more complicated example of a Markov process and transition and state transitions with probabilities, right? Let's say that you have a leg day in gym. All right. This is, I think, mostly like fitness enthusiasts would relate to. But yeah, you let's say that the initial state is that you are in bed, you are in peace, and there is a 0.9% probability that at each time step you would choose to stay in bed and in peace. And you know what? I don't blame you. So let's say that on the chance that you do decide to get up and you make it to the gym entrance, you're still not in the gym yet, all right? There is still a 0.1% chance that you will stay at the gym entrance because you're indecisive of what to do next. Then you come up with the idea that you have two options. First is you can go and train legs, or you can have Sunday on a leg day. So the probability of doing leg day is 0.2 and to have a Sunday is 0.7. So odds lie heavily in the favor of having a Sunday. But don't worry, even after you go to gym, you will still be able to, have a Sunday. That won't be a problem. And after all of this, you deserve rest. All right. So, with a probability of 0.5, from the gym, you will go to sleep. And from Sunday, you're surely, like with probability equal to 1, you're going to go and crash. So, this is a very simple example, or let's say a little bit more of a complicated example than we saw in the last, of a Markov process. I want you to understand, I want you to just take a step back, pause this, and see that what is a Markov process, what does a Markov process comprise of? It comprises of states and probabilities. And each state transition has a probability associated with it. And I think it's very uh, intuitive to also understand that each transition for each state would always add up to 1, right? Like for in bed, in peace, this state has two transitions, 0.9, 0.1 adds up to 1, right? When you're in the gym, you have two probabilities. You can either go to sleep, you can either go to have a Sunday, 0.5, 0.5 adds up to 1. So I want you to notice these little things because I think it will help you in the next part of the video. So there is a side quest I'm giving you. What you have to do is you have to create a probability transition matrix P for the five Markov states. All right. So what you can do is you can a matrix is like rows and columns, right? So you can make one. You can on this side, on the vertical side, you can list all the states, and on the horizontal side, you can also list all the states, and you can just create a probability transition for each state for m comma n, for this expression will make it more clear. So for p ss dash of that transition matrix, it will denote the probability that at time plus that the state at t plus 1 is s dash, given that the present state is s. All right. So pause the video, make the probability transition matrix, and try to match it with the next frame. Yeah, so your transition matrix should look like this. Now, if you look closely, the fact that I said that each state would have each state's probability transitions would sum up to 1. So you can see that each row here sums up to 1. So we do not worry about the probability of transition states in terminal states. So because of course, where do you go from a terminal state, right? So we do not worry about that. And that is what I want you to take away from a probability transition matrix in a Markov process, right? So let's just summarize what a Markov process is, right? We can easily define Markov process as a tuple of P and S, whereas P is the probability transition matrix and S is the set of all Markov states, right? So next up, I think we'll be looking at Markov reward processes and just a little bit intro to them to make sure for the next video you're geared up for all the information you would need to understand the concepts. So what is the Markov reward process? So far, we have covered what a Markov process is, right? And what do you use to characterize a Markov process? You use a tuple of two variables, which are P and S being the set of all Markov states comprising the process, P being the probability transition state matrix, right? So we'll be transitioning from a Markov process to a Markov reward process by introducing two new variables to the tuple. The, two of them being R and gamma. So R is the reward which is associated with a particular state, and gamma is the discount factor. So what do I mean when I say that reward R is associated with a particular state? Let's just go back a few slides, right? Let's say that being in bed and in peace has a negative reward, and being at the gym entrance has zero reward, and actually going through with it and training your legs at leg day in gym has the highest reward of all of these five Markov states. So this is what I mean when I say that a reward R is associated with a particular state. Alright? And to understand what gamma or the discount factor means, we will understand two very simple concepts: episodes and return. So let's just start with episodes. So to take a very simple example, all Netflix series are broken down into episodes, and each episode contributes to the bigger picture or to the bigger goal of the story, right? So the bigger goal is divided into smaller ones, and each of them is characterized into an episode. So same is the case with episodes in reinforcement learning. Let's just take an example of what an episode for Robbie would look like. Let's just first label the entry and exits of the maze, all right? And the initial state of Robbie would be when he enters the maze, and the terminal state would be when he exits it, all right? Let's just say that the between the initial and the terminal state, between Robbie navigating the maze once in its entirety, would be one episode, all right? So episodes can be considered to be agent environment interactions from initial to final states. Now we'll move on to understand return. So return at a timestamp t is equal to the sum of discounted rewards from timestamp t onwards to the end of that episode. So let's just say that, so this expression here, you can actually observe that as the timestamp would increase, the power of gamma or the discount factor here would increase. So look a little bit closer into what discount factor actually means. All right. So discounted rewards are actually discounted by this factor, which lies between 0 and 1, and is actually a quantitative representation of the priority or the weight we are giving to future rewards. So you can have a bit of an intuition by looking at this expression here. What if I put the discount or the discount factor as 0? Then the only weight or the only priority will be given to the next immediate reward. So it will be a very impatient, or let's just say a very impatient return function. And a very patient return function would give weights to future rewards as well. All right, let's say if my gamma is 0. 0.9, then I am thinking far ahead. I am giving weights to future rewards as well. But why even keep it 0. 0.9? Why just not keep it at 1? Why discount at all? So let's just imagine what will happen if we don't discount. If we don't discount, we might get infinite returns in a cyclic Markov process. So let's just say we have taken a look at Markov processes, what Markov processes look like. Let's just imagine what would happen if a Markov process is cyclic, which means that the return would always increase. And if we don't do anything to scale it, then we will get infinite returns, which we can't scale, right? Which is not suitable for comparing or even understanding which state is better, which state is worse, which timestamp was better, which timestamp is worse, right? So we can also prefer immediate rewards with the low discount factor. As I said before, if we keep the discount factor as 0 or close to 0, we'll be creating an impatient reward function or the return function, which will prefer immediate rewards. So an undiscounted reward processes with gamma equal to 1 can also happen if all sequences terminate. So this significance of termination is perfectly correlated to infinite returns. We get infinite returns in cyclic Markov processes because they don't terminate. They keep on going in cycles. But if we are certain that all sequences will one or the other way will terminate, we can have undiscounted Markov reward processes. So two types would be with gamma close to 1 leads to far-sighted evaluation of a return, and a gamma close to 0 leads to myopic or short-sighted evaluation of any state or timestamp. Thank you for your attention, and keeping these concepts of episodes, return, and discount factor, we will be moving on to the next video of Markov reward processes and actually understanding how we associate it with the leg day gym problem. Thank you.